Hey there, in this video we are talking about random access files in C++ programming, and this covers sections 12.9 and 12.10 in the Gaddis textbook. So this is a very advanced topic actually, and to make a long story short, random access file handling means you can jump to any point in a file that you want at any time. This is going to look quite a bit different than how our file handling has before, and we'll think a little bit about why you would want to use this in advanced type situations. And it's kind of an interesting subject, I think. Okay, so random access files. There's two ways that you can access files. There's what's called sequential access, and then there's random access. Now, everything that we've done up until now has been sequential access. And what that means is it means that we are assuming that when you open a file to either to read or write, you're going to start at the beginning and you're going to go through the data in order. So you're going to be dealing with byte number 1, 2, 3, 4, 5, 6 in exactly that order. There's no question about it, and there's no other option. So that's fine. It's very predictable. It's very easy. The computer is taking care of where the read head is currently. You read a byte and immediately advances one byte later. We don't have to. We can take that for granted. We don't have to do any work to understand that. But the downside is that if you have a very, very long file, and let's say you're only interested in the 100th structure, you're going to have to read structure number 1, 2, 3, 4, 5, even though you're not going to use them, all the way up to 100 before you actually get to the structure that you're interested in. So in some cases, that can be wasting a lot of time on the CPU and also actually putting a lot of stress on your hard drive when you don't really need to. So the thing that we're looking at in this particular lecture, the other alternative, is what's called random access. And if you use this, you're going to have to do a little bit more work as the programmer, but you will be able to jump directly to whatever byte in the file you're really interested in. So if you have a binary data file with a bunch of structures and you really only need number 100, just jump immediately to structure number 100, read that in, and deal with it. And in that sense, it'll be a lot more efficient, again, for larger files. And we'll just think about that for a second. So when we use the word random in these kinds of features, we do not mean from the user's perspective, right? From the user programmer's perspective, it's not like you're getting random, unpredictable data. But this is from the computer's perspective, is that the user is permitted to ask for any piece of data that they want. So from the program's perspective, it can't use any shortcuts. It can't use what's called caching. It can't temporarily save stuff in the buffer, expecting that that's the next thing that's going to happen. From the computer's perspective, the user can ask for whatever they want. And from the computer's perspective, that looks random, but your program needs to serve up that information instantaneously, no matter what the user wants. And this is similar to the name of our memory system, RAM, right, which stands for Random Access Memory, the exact same idea. The programs, the CPU or the user, can request any byte in the memory system at any time, and it's obligated to access it instantaneously. It can't cache, it can't take shortcuts. It has to make all of those bytes available all the time. Now, there are some systems in the world where that's not actually how it can work. Like a hard drive has a disk that has to spin to a particular location. So you can't literally jump to any location instantaneously. If you have a big tape drive that some people save lots and lots of data on, actually a spinning tape drive, you can't actually jump to any place in the tape you want at a time. You've got to spin the wheels to get to the right place on the tape. But from the perspective of a C++ program, where you can kind of pretend that that's going to happen, and the compiler and the system is going to take care of it for us, and we can pretend that we can jump any place that we want. And here's how that's going to work. Okay, so the main functions we're going to be using for this are called seekg and seekp. Seek seeks a particular byte in the file that we want. And these are object-oriented functions, so you're going to have an fstream object that you've opened up, and if I have an fstream called myfile, I'm actually going to be writing myfile.seekg or myfile.seekp to make these functions actually happen. So seekg, which is short for seekget, that's the function that gets used for files that are open for input, right? An input file is something that I'm getting information out of, so they called that seekg. And seekp, which is short for seek put, That's the version of the function you need to use when you have a file that's open for output. Right? An output file is something where I'm going to jump to a particular byte in the file and then put some data into it, write some data to it. And either one of these go to a specific location in the file. Now, both of these functions take two parameters to state how many bytes you're moving and also where you're considering the starting point to be. And that's on the next slide here. Okay, so seekg and seekp have these two arguments. And here's the details about that. The first argument is the offset, which is the number of bytes you're going to jump. Now, again, the idea of these functions is to use them on really giant files, like maybe a supercomputer, a huge database that's got trillions of bytes of information in it. So this was set up that first parameter is not an integer, it's a long integer. And of course, on our systems, the long int is actually the exact same thing as the normal int. But what we said in our review lecture, the very first lecture of the second semester, is that that can vary on different types of systems. So if you are on a supercomputer with much larger storage, you can have a long int that's a larger size and can store much larger numbers to indicate the offset or the address into a really huge file. Okay, so a long int there. And that's going to be one little thing we have to keep track of. The second argument is a mode flag about where, granted you're moving this number of bytes, where you're counting as the start of your jump. And there's three options. There's ios : BEG for the beginning of the file, really byte number 0, I would say. There's ios : end for the end of the file, or there's ios : CUR for the current location where you are right now in the file. And any of these three things are options. So here's a couple of examples here. So if I presumably have a file that's already been opened for input called indata, I can call indata.seekg, and here's my first argument, 25L. Now remember, that first argument needs to be a long int. Well, if you specify a long int, the literal has to end with an L to indicate this isn't a normal integer to match up with what this function expects. This is meant to be a long int. So you've got to write 25L to indicate the number 25 as a long integer. And here we're using ios BEG as the mode flag. So you're counting from the start of the file. So if the start of the file is byte 0, you're going to move up to byte number 25, which is technically the 26th byte in the file, again, because you're going to start counting from 0. Okay, so jump up 25 bytes from the beginning of the file. Another option down here is, let's say you have an output file, and you can mix and match either of these functions that you want. Let's say you have an output file called outData, and I want to jump to a particular location. I've already done some writing. Okay, I've already done some writing in the file. I'm some number of bytes into it at this point. I can write outData.seekp, and you notice that the first argument here is -10. That offset number can be positive if you want to jump up further into the file. It can be negative if you want to jump backwards from where you started, back towards the start of the file. So here you have the number -10, written again as a long integer with that L notation. And here the mode flag is ios : CUR. So you're jumping 10 bytes back from the current location, wherever that is. Okay, so a bunch of kind of nice options there that you can use. Again, need that long integer syntax because we're really kind of thinking about if I was on a supercomputer and I had much larger files, I would need to deal with larger numbers than you're seeing in these examples. Okay, let's see a specific example of that. So this is program 1217 in the book, and it's going to be doing some random access file handling with seekg, I believe. So we're going to assume, for the purpose of this example, that we have a file called letters.txt. You can see down on line 11, that's what's getting opened up here. Opens up letters.txt. And the example that comes with the book, letters.txt, is literally just the 26 letters of the alphabet. So it's just A, B, C, D, E, up through X, Y, Z. That's the contents of letters.txt. So let's go through this and see if you can predict what byte, what character is going to get pulled out of that text file as this program proceeds. So you have a character called CH. We're going to be pulling out 1 byte at a time. And we open up this F stream to connect to letters.txt. In this case, this is a text file. Don't forget that you can use all these functions with binary files to get whole structures, but for our initial example, we're just going to work with simple characters. This is being opened for input. So the first thing we're going to do here, like the comment says, is move to byte number 5, which is actually the 6th byte, starting from 0. Move to byte number 5 and read the character there. So you call file.seekg, right, number 5 as a long integer, from the beginning of the file. So if this, look up at the top there, if this is the contents of letters.txt, right, and then once you jump to that location, you call file.get, you take that byte, you store it in the character ch, and you're going to print it out. So if you jump 5 bytes from the beginning, remember the A is offset 0, right, that's index 0, and you jump to location 5, right, get that particular character, what would it be? Maybe pause the video and see if you can answer that. Okay, so if the A is offset 0, that's 0, 1, 2, 3, 4, 5, that ought to be the F, right? And I think from that particular get, you'll be seeing lowercase f. You just jumped where the F is, just got that one character. Okay, let's try a couple other things. So you have that same file open there. The next thing we're going to do is we're going to move to the 10th byte from the end of the file and read the character there. So here we're calling file.seekg. The offset is -10, okay, but we're counting from the end of the file. Okay, and then once we jump to that location, we'll get that character and we'll print it out. Now for this, right, the little thing you to remember is the end of the file is actually a special marker, kind of like a null terminator, that's after the visible characters. So the end of the file, the end of file marker is actually 1 byte after the Z. So if you move backwards 10 bytes from that location, where would you be then? What byte would you pick up? Again, pause the video and see if you can answer that. So I think counting from the end of the file that's actually after the Z, if you move back 10 bytes, you'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think you'd be at the Q, I believe. Just recount that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm pretty sure that's the Q is what you'd see. Right, 10 bytes forward from the end of the file. And then at that point, what it says we're going to do is we're going to move to byte 3 from the current position and read the character there. So you can see on line 27, we're doing file.seekg, and we're going to move 3 bytes, counting from the current location, right? And then once you make that move, you'll pick that up with the get function and you'll print it out. Now, the thing that you got to remember here is that when we read the Q, right, whenever you get a byte, the default is you move forward to the next thing. So when we picked up the Q, in addition to doing that, the computer automatically moved the read head to the next byte over, because that's normally how it works with sequential access. And right this second, you're actually sitting on the R. So when line 27 happens, I'll let you figure that out, right? Pause the video. Where would you be then? Okay, so if we're actually sitting on the R as a result of getting the Q, and line 27 moves us 3 bytes further down, 1, 2, 3, I think we'd be at the U, right? You'd pick up the U and you'd see that. You just see that. So all told here, this program jumped to the F, okay, from the beginning, and then it jumped over to the Q, which is 10 bytes forward from the end of the file, and then it was on the R, and you move 3 bytes further down from there, and then you got the U, and that's what happens with this program. You can jump wherever you want, right? There's a whole lot of options there for where you can go. Here we're testing this out on a text file and just getting one single character at a time, but this could be a binary file where you're jumping and you're grabbing whole structures with your binary file handling like we saw last time. So a lot of powerful options you have now. Okay, so a couple of details about that is it is possible if you give the offset a really large number, you might try to jump all the way past the end of file at the end of the file. Or like a big negative, you'd try to jump past where the beginning of the file actually is on the hard drive. Now for safety, the hard drive's not going to permit that. If you could do that, you'd be in the same situation with a buffer overflow where you could potentially overwrite information in other files. You could actually trash the whole hard drive. And so the system is not going to permit that. But what's going to happen is it's going to set this error flag in the file, that EOF end of file error flag. And once that error flag bit has been set, none of these functions work anymore. So seek G won't work, seek P won't work, none of them work. But if you know that happened, if you can detect that, and remember you can test that with the EOF function that we talked about earlier actually, if you find that's the case and you need to fix it, you can use that clear function. So if I have a function called grade file and I've hit the end of the file and I want to keep doing more work, I can call gradefile.clear. That clears out all of the error flags, including the EOF one, and now your seek G and your seek P will work again. And one thing you might recommend doing is just go ahead and jump back to the beginning of the file and start all over again. So at that point, you could call gradefile.seekg. I'm going to jump 0 bytes from the beginning of the file, which is obviously the actual beginning of the file itself, and then you can do whatever you want again. Okay, so again, if you hit the end of the file, make sure you clear it out or your seek functions won't work anymore. Now, the other two functions that are available here, and for my students, I would recommend maybe make a little note card of these functions we're dealing with in this lecture because we're going to need them in the next lab that we do. The seek G and the seek P were the user telling the system what byte I want to jump into. But maybe you're in a situation where you don't currently know where you are. And so these functions here, tell G and tell P, do the reverse. So maybe if you had a while loop or something like that, and you did some reading and you're not sure where you are right now, you can get the system to report where it currently is in the file. How many bytes deep am I into the file? So once again, you have one for input files and one for output files. Tell G, which is short for tell get, is the function you use to return the current byte position in your input file. So tell G is going to return a number. Now remember, the offsets are counted in terms of long ints. So if you're going to store the return value in something, you need to declare a long int. If you don't do that, hypothetically, you might have overflow. You don't want that. Here we're declaring a long int called where am I, and we're setting where am I to the result of a call to indata.tellg. These functions don't take any parameters. They're what we call accessor functions to an object like indata here. And where am I then will have the number of bytes that you are into that file. Tell P is the version for an output file, again short for tell put, a file that I'm putting data into. And so once again, I would need a long int to store that, and I can call outdata.tellp, and now I know how many bytes I am into my output file. And now that I know there, I can move forward or backwards appropriately according to that. So a number of nice options. Okay, now the other thing that is pointed out at the end of this chapter is that you can have a file that's actually open for both input and output at the same time. Most of the time, up until now, we've had a file that's either open for input or output, one or the other, but it is an option to have it both. And so what this would support you doing in practice is, again, let's say I have a giant data file. It's got billions or trillions of bytes or structures in it. And what I want to do is I want to edit one of them. Like maybe I'm working at Amazon. I've got 100 million customers, and customer number 2 million needs to update their phone number. Okay, so obviously I don't want to read in a million structures that I'm not going to do anything with. What I want to do is I want to jump to structure number 2 million, just read in that structure, right, edit the phone number, and then write that back in place without modifying anything else in the data file. So by having it open for input and output, you can do that. Jump to that structure, read it into memory, modify it, and then write it back out into the database on your giant hard drive or something like that. And that's something that they actually do need to do when you're managing a giant database. So that's what that would look like. You'd make a file stream object, an fstream object, maybe call it grade list. If I've got a database that has all the grades in the entire CUNY system since CUNY ever started, right? That would be a huge database. So you would give that file stream a name like grade list here, connect it to the file on the hard drive grades.dat, and here you can see we're using both the iOS in flag and the iOS out flag at the same time, and that's perfectly permissible. So this particular file here, you can do both input and output with. Now that would be an example where you're working with a text type file, but you can also do this exact same thing with a binary file and get whole structures like that at once. And that's something that you would potentially want to do there. There's a nice example in the book you can check out and see if that possibly works. Okay, so random access file handling. Again, that's a legitimately advanced feature, and that is there again to handle giant databases on supercomputer systems that have lots and lots of data that would take too long to read the whole thing. Now, let me admit the following. I have never actually used these features in an actual program that I have developed myself. The programs that I make myself are not that huge. I have data files that might be some number of megabytes, like some number of million bytes. And so my general custom is that when my program starts up, I have an array and I just read all the data all at once off the file, put it in memory, close the file, and just hold it in memory, which is super, super fast for all the work that I want to do while my program's actually running. Okay, so my memory system is fairly large. I think it's currently 16 gigabytes, so I can hold 16 billion bytes. And if I need to load in 5 or 10 or even 100 million bytes, no problem. Just store it in memory the whole time my program's running, perfectly fine, super fast, very, very simple. But if I was working, again, on a supercomputer, I was working at the Super Collider facility in Europe, and they produce terabytes. They produce trillions of bytes of data on a daily basis. That's too much data to load in to a memory system. You can't read it all in like I normally do with my programs. So if you were in that super advanced situation, you would have to use this random access type system to go find the specific structure that you want, just load that one into memory, make some edits to it maybe, write that back out to the correct location in your giant database without reading everything else, without changing or modifying anything else. And that's the efficient way you would do it with giant databases, which admittedly is not something I've ever actually done. But it is part of the C++ system. It's important to know about that if you ever do work at NASA or Amazon or a Super Collider facility or something like that. You know that it exists in C++ and it is an option for working with much larger databases. And I think that's important to know about. And that's what it's there for. Okay, so we are at the end of chapter 12, and this also marks the end of part 2 of our second semester programming course. So my students, I would recommend read book chapter 12 and see all the details here about that. Test yourself with the review questions at the end of the chapter as normal. My students will have a programming challenge on file handling from chapter 12. And look, I'll say the random access files are not something that I would give as an assignment. They're not something I'm going to have my students actually code up on. That's a little bit ridiculous, again, because to make that worthwhile, you would need a giant database larger than any of the computers that we have available to us. But you ought to know about it. Again, I would ask possibly multiple choice questions about that. So the programming challenge from chapter 12 will be something a little bit simpler than that. And then as my students get prepared for their next in-class test, they can see practice test 2 that's on our learning management system. And in addition here, I've got a couple of programming challenges that are optional additional practice that would be really good practice to get ready for that. And, at this point, we have a fairly nice package of things you can practice with these challenges here, that everything in this part of the course works very nicely together. We've looked at strings, basic C strings in chapter 10. We've looked at structures in chapter 11. And we've looked at file handling, both text and binary files here in chapter 12. So among the things you can do now is you can make a structure to hold a record very efficiently. And it's very elegant. It's very efficient if your structure has a fixed size, and you can figure out what that is for binary file handling. And if the string fields are C strings so that they are fixed in size, that works really nice. And then you can write that kind of information efficiently to a binary data file with one single line of code. And so your knowledge about fixed size C strings and structures and binary data files just work really, really super nicely together. So these optional programming challenges, you're probably going to be practicing all of those things, which will be great. And then the next time that my students get together with me in person, we're going to do this lab on random access files, get a little bit more practice about how that works. It's a very small, very short little program, and there's going to be a text file called proverb.txt. And what I would want to do is load that up in a text editor, just read it, see what the contents are. And what this program does is, I think there's just a couple lines of code we have to fill in, and it actually asks the user, do you want to jump forward in the file? Do you want to jump backward in the file? Where do you want to jump in this file? And I will show you the particular character at that location. And the user gets to jump up and down wherever they want, and kind of prove that you can actually jump any location you want immediately in a random access file. And maybe there's like some improvements we could make to that program. Maybe there's like an error message that we could add to help the user know what's going on there. And of course, we'll test that program with that proverb.txt and make sure we understand that. Okay. So now when we come back to part 3 of the course, we're finally going to start in on object-oriented programming in chapter 13. And that is actually the #1 objective for this second semester programming. In fact, it's the primary goal all along for our entire first year of programming. Everything we've done in first semester and second semester up to this point has really been getting the building blocks, the fundamentals of programming together so that we can put them all together and make our own objects in what are called classes and really develop ourselves like a professional programmer would for larger programs with what's called object-oriented programming. And so I've been anticipating that for some time, and I'm really excited to finally get to chapter 13 and finally start doing object-oriented programming, which has been the goal all along. So I really hope that sounds interesting to you as well, and I'll be very excited to do that next time, and I'll see you then.